take this on one of those handouts.
Yeah.
Oh, I've given you guys so many handouts. Complex conjugate theorem. Now, all it comes down to, if you see something like this on the exam on Wednesday, is if you see an answer come out that looks like this, takes this form, what can you quickly say must be another zero? A minus bi. They come in pairs. So if I should ask you to find zeros, and I list a few zeros for you first, I may say, okay, 2 plus 4i is a 0. Now find the remaining zeros. Automatically, this one, you'll list quickly. That's another 0. And they come in pairs. And they're called conjugates, complex with the I in them. Okay? And then, of course, you have to find the others by using rational zeros theorem, so forth and so on. Descartes' rule of signs. Egg did a beautiful job in the presentation at 4 o'clock on all that. Okay, guys? So complex conjugate theorem. If now, here we go. If you should see this, I thought about this before I start my lesson here. The intermediate value theorem or property. Does anyone recall what was that all about? Lisa.
So it's about like B over Q, which is Q over P.
Now this B over Q, that's rational zeros theorem. This is intermediate value property or theorem, which sometimes is helpful. And in fact, I mentioned that to you in class doing a problem once before. Does anyone recall anything about it? Yes.
The example we used was on a graph where we had 2 points was in the positive and another one was negative, and basically we were guaranteeing that a point in the center would cross 0 or cross the x-axis.
Is that about like, is that about finding the holes?
No.
Graph?
That's all together. Intermediate value theorem says, guys, this right here. Illustrated, it says if you have a graph, it looks something like that. And let me do this right here. If I can do this. And you have a point given to you, maybe, find a nice one here. Here we go. Let's say a point here and a point here. Position like that. And the graph connects those two. Am I guaranteed when I connect those two, am I guaranteed I will at least cross over the x-axis at least once?
Yeah.
Which tells me there's a 0 there. Now, how am I assured that's going to happen? Anyone tell me, what would you be looking for? Samantha, help me out.
So basically, like the intermediate value theorem, it just tells us how to find a real 0 between 2 specific points. So what we would do is, using those 2 points, we would find, for example, like f of x. So if it's like f of 1, we plug it into.
Okay, let's say this right here. That's beautiful. Let's go ahead and label this point. Let's say it's out 1, down, I'm going to say down 2. Let's say those are the coordinates of that point.
Okay, so then it'd be like f of 1.
F of 1
Equals,
negative 2.
Yeah.
That's what it says. Now to label this other one, she's telling me exactly what I'm getting one here. Now I can label this other one, guys. I notice it's above the x-axis. I'm going to call it maybe out 4, let's say up 3. Those are my points. And they got to be connected by the curve. The curve's got to connect them. Now how am I assured when they're connected that I am going to at least cross the x-axis one time somewhere in between them? That's why they call it intermediate. Somewhere in between, I'm guaranteed I'm going to cross over. And therefore, there's an answer there. And you may want to start searching for that answer. What guarantees me that that's going to happen? Yes?
I would assume because the y
Beautiful. This is below, I heard him say negative, that's below the x-axis. This y value is, where am I? Right here. 3 is above. How on earth can you go from below to above and not cross over? Must you cross over if you expect to join those 2 points? If this one's below, it's below at -2, it's below the x-axis, and this one's what, above 3, right? There, is that what you're talking about? Yeah. So one's below, one's above, and you gotta connect them, and the only way you can connect them is you gotta cross the x-axis. As soon as you cross the x-axis, what have you discovered? A 0. Now, what does that tell you on the test on Wednesday? You say, Professor, you mean when I start testing, and I do all this business, and I know how to use synthetic substitution, and I test maybe 3, and all of a sudden I go through my routine, and I hear it didn't work, Professor, but I got a 4. Which means you have that, but it's not 0. Then you get a little frustrated, so I'm going to test something else. Let's test maybe 1. And you go through your routine, and this time you get -6, which means 1, -6. Is there a sign change between those 2? Is this one above and this one below? So that means you have now caught an answer in between. So now you may start saying, oh, this tells me it didn't work, but there's an answer caught between 3 and -1. And you may go back to your choices of P over Q and say, oh, maybe something caught between 3 and -1, maybe 1 works. But we're guaranteed at least 1 does work in between, as long as you get that sign change. Samantha, thank you. Sharon, thank you. And those explanations. Guys, you with me? So it's called intermediate value theorem, just in case, and I know I'm doing this because I know how frustrating it is when you do synthetic and it does not work, does not give you a 0 at the beginning, which you would love to say it did, but sometimes it does not. At least there's still a benefit. It's not a 0, it's not a 0, but since those signs change, there's something caught between these 2 that will work. You're guaranteed. So you now try something between 1 and 3. Like 2, right? Try something caught between 1 and 3. That's why there'd be some possibilities of numbers caught between 1 and 3. Try one of those numbers. But something in between them has to work. This intermediate value theory says at least 1. Could be more than 1 that works. Okay. Guys, I'm worried. I'm worried about the test first. Now I can just do so much. And Mr. Park can just do so much, and those workers in the math lab were working so hard down there. I just stopped to see how many students were down there. Quite a few students were down there. We can just do so much. A lot of this is going to be up to you. I can do some of the most amazing lessons ever. Mr. Park can do his tutoring in the math lab. Those working in the math lab do beautiful work down there. And yet you might find out, oops, I did not pass the test. And then you look on the schedule and say, oh, Ramsey's teaching the same class during winter. I don't think you guys want to see Ramsey again. Not for Math 2. I'll find you in Math 7, though. I'll find which class you're in Math 7. I'll find you. I've already found 3 or 4 of my previous students. See how they're doing. I'll find you. But I don't think you want to do a 6-week course with me. Can you imagine doing this in 6 weeks? Not 16 weeks like you have, 6 weeks. Doing all this work. It's a different situation altogether. Okay. Okay, guys, we'll jump into it. I'm going into rational functions. Here we go. Now, this is the ending of chapter 3. By the way, you notice on that handout for the review for the test, I'm not including rational functions. If I did, more than likely the test would be 4 hours. I don't want that. You don't want that. Okay, so no rational functions on this particular exam on Wednesday. Now, let me see if I can find some good markers here. Here we go. Rational functions. Guys, we use R for rational, R of X, and they're expressed as a ratio, rational ratio fraction. Most textbooks write them as P of X over Q of X, and of course Q of X cannot be 0. That's what a rational function looks like. And then we're asked to sketch it. That's what I sort of talked about on Wednesday of last week, rational functions. By the way, I think I did give you a handout on rational functions. Please tell me I did. Yeah, because I want the students to start reading some from that handout. Then we talked about a vertical asymptote. You remember those words from last week? Maybe a horizontal asymptote tonight. Crossover points, all that business. There's so much going on in one problem. I'm telling you, a rational function could be an exam. There's so much going on. To just get the sketch of it. But to lead into it, I will point out what I consider the most simple rational function out there. I'm going to start out with this one. 1 over X. That's a fraction. P of X over Q of X, and I did not let Q of X be 0. Okay, I'm not going to let X be 0, so it's 1 over X. Now, if it's a rational function, there's a sketch for it. Now, some of us may, I thought I brought my, some of us may recognize what 1 over X looks like. Does anyone know what 1 over X as a sketch looks like right now? And we'll have the most simple rational function sketched in no time. Lisa, describe it for me.
Looks like a hyperbola, so from the top left, the graph is,
Okay, got you. We got the grid. And Lisa, you're describing for me?
from the top left,
You mean like in the first quadrant?
no, from the
Right.
first
Here.
Oh, yeah.
I'll lead you into it.
And the
Third quadrant.
is decreasing, it should be decreasing, yeah.
There's the graph. I think, if I'm not mistaken, I think that's on a sheet I gave you guys weeks ago as a parent graph. I think that was on that page. And I think we called it then the reciprocal function. Like take the reciprocal 1 over X. I think we call this the reciprocal function. Guys, that's the most simple rational function. It looks like this. And I'll point out right here, do not let X be 0. Can I have a 0 in the denominator? And by the way, how does that graph show me I was not intending to let it be 0? Now, what did I do there to show don't let X be 0 because that thing becomes undefined? What did I do, Sophia?
It doesn't touch the x-axis.
Here we go.
The x-axis.
It's not going to touch the x-axis, but for the reason I'm looking for the other, it does not touch the what?
0.
The 0. And you know where 0 is, right here, 0. In other words, it does not touch this, the y-axis. That's 0. I can't touch it. If I touch it, X becomes 0. And we said, no, X can't be 0. So that's why you got to put that line there. I had to usually break it. And this is known as a vertical asymptote. And a little strange spelling here. A vertical asymptote. Now, I think, let me get back to Sophia. Sophia, you pointed out, Professor, it looks like there's another line that you have the graph getting close to, but you're not touching it. Besides the vertical, there's a what?
Horizontal.
Horizontal, the x-axis. So down here, I also pointed out, in this one, you cannot touch, in this case, the x-axis, and this is known as a horizontal asymptote. We've got vertical asymptote, horizontal asymptote, and there's my graph. And that's the basic reciprocal function. And it's called a rational function here. You guys with me? No problem. Since I'm looking at it right now, before I jump into something a little bit harder, guys, can I help me out, please? Can I have someone please quickly tell me what's the domain on my orange graph? Or the function? In integral notation, from left to right. Negative infinity, up to zero, not including zero, union, zero, infinity. That's my domain. Range, not exciting, the up and down, you're gonna find the same thing. Negative infinity up to zero, union, zero through infinity. There's my domain, range, no zeros here, no x-intercepts. That's strange, no x-intercepts here. No y-intercepts. This is a really strange one. But it looks like that, and you could plot points from a table if you wish to get that orange curve there. And that's the way it looks. Now, someone with a handout. I wish they all were this easy. I need part B. Who has the handout available?
This one?
Yeah. Tell me what the very first function at the bottom is.
Oh, x minus 1.
Okay, R of x?
R of x equals x minus 1 over x squared minus 4.
Now we got problems. By the way, that is a p of x over q of x. It takes this form up here. So this is a rational function. What I would, yes?
How can you tell on the parent function the y has a vertical asymptote or the horizontal?
What's it now?
How can you tell it has a
Beautiful, you can't tell until we start reading from that handout. Got you. Okay, now, we have this one to look at. Quickly though, I could point out with what we're discussing, if she gave this to me, I know immediately, you cannot let this be zero. That's what we said here. The denominator can never be zero. Which might help me out before we actually jump into it, this factors. Now, can anyone tell me, before I really jump into it and try to get the graph, what should be happening at 2 and negative 2 based on the fact that that cannot be equal to 0? What's going to happen?
There's going to be some vertical asymptotes.
That's where the vertical asymptotes show up. So if I go to the grid right now, at least, I know that at 2 and negative 2 are some vertical asymptotes. To show no, 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 you cannot let the graph touch those. That's where you go out to 2. That's down here, out to negative 2, up to here. So that on a marker to work for me. And I'll go ahead and place a vertical asymptote here. A vertical asymptote here. Those are done. Now the question that my student had. Professor, you've got the vertical asymptotes out of the way. I heard you mention the words horizontal asymptote. There could be a horizontal line that acts as a guide or an asymptote. He says, it was easily seen on the first example. But here, does anyone think they know before I have a student start reading for me? Where might that horizontal line, which over here was here, where might it be, because it could be at various places, acting as a horizontal asymptote. I see hands going up already. Lisa, tell me what you think.
I'm thinking if the y should be.
I was just telling you the location. Where is the horizontal asymptote located?
X equals 1.
Use the to begin.
X equals 1.
Okay. Where do you think the horizontal asymptote is located?
I don't think there's a horizontal asymptote.
Okay, now, beautiful, that's a discussion. One student says, I don't think there is one, Professor. Another one tells me, she says it may be up at 1. You go up to 1, Professor, which could be, and draw a horizontal line. And that's gonna be an asymptote. And help me sketch this thing. Yes?
would it be the y-intercept?
So again?
Would it be the y-intercept?
The y-intercept? Oh no, that's a separate thing altogether. Okay, so one student says, there is no horizontal asymptote, professor. There's not one of these horizontal lines that my graph is going to follow and get close to but not touch. Okay, and then another student said, maybe it's up at 1, professor. And then a student asked me earlier, said, professor, how do you find a horizontal asymptote to begin with? I don't want to sit here and just guess. Okay, this is where the reading takes place. Okay, here goes. Who would like to read for me? Who has a handout?
Oh.
Yeah, go up to the top. Do me a favor. They give you some extra credit points, maybe not. Okay, but go up to the top. And now, are there some steps there?
Yes.
Okay, here we go, guys. We've got all these steps. Woo! Get ready. Tell step 1 in approaching a rational function. What should I do?
Step 1 is find the domain of R of X. Do
Yes.
not cancel factors in step 1.
That's good. They want us to find this right now. And I would say X cannot be what? 2, -2. That's my domain. If you want to put this in interval notation, my domain will be, if I ask for an interval notation, a negative infinity up to a -2, union, -2 up to 2, union 2 to infinity. There's my domain, and I give you partial credit when you finally see this next Wednesday. On your quiz, because next Wednesday's quiz is only one problem. I'll tell you that in advance. There's only one problem on the next quiz. It's a rational function. It's gonna take some time.
That would be quizzing.
No, we're talking about, right, we're gonna get this done first. Now, read step 2.
Step 2 is simplify. Write R of X in lowest terms.
Okay, here we go now, because this is difficult. She says, now, professor, go back to your function and write this in simple form the best you can, professor. Let me do it up here, guys. It's step 2. R of X, the best I can do is this. That's step 2, done. I notice nothing cancels. Sometimes things will cancel, and that's another issue. Thank goodness on this one, nothing cancels. That's step 2, and you get partial credit. Now tell me step 3 is what?
Name the intercepts X and Y of the graph.
Let's pick those right now. X-intercept, Y-intercept. Let's get the X-intercept out of the way first, guys. How do you always find an X-intercept?
Make Y 0.
You set the Y equal to 0. Okay, if I set the Y equals 0, that's the R of X. You got this. I'm going to set that equal to 0 and attempt to solve it.
It will be.
I would just quickly cross multiply. You think this 0 is 0 over 1. And a quick way is just multiply these two together, and then cross, and then multiply these two together. And guys, you're going to merely end up with 0 is equal to what? X subtract 1? Solve easily. Oh, look at that. There's my X-intercept. There's my X-intercept, step 1. I'm going to list it as an ordered pair. So my X-intercept is 1, 0. This will play a part here shortly. That's step 3. She asked me also to find the Y-intercept, which I haven't found yet. That's my X-intercept. Now, I'll give you a little hint. One of my students in one of the past semesters said, Professor, when they asked me to find the X-intercept, I see what you did. You set the R of X to Y equals 0 and did your business there and cross-multiplied. He asked, is it merely just taking that numerator? Does it really come down to that numerator set equal to 0? Is that what it came down to? It always is. So if you want to find the X-intercept on a rational function, just take the top part, the numerator, and set equal to 0. And that would be a quicker way to get to where you want to go. I did the whole business there. Okay. Now the Y-intercept. Here we go. Y-intercept.
-1/4.
I think I'm hearing it. Let's see if it is. Now Y-intercept's a little bit easier because you find R of 0. Go back and replace those x's by 0, guys, right here. You see what's gonna happen, they drop out, and you end up with a positive 1/4. I'm gonna write it like this.
Oh, yeah, 1/4, yeah.
There's my y-intercept. Now, do I have a sketch yet? No way. I'm building up to the sketch. I just don't have it yet. But all that's partial credit. Now, what's the next step?
Determine the vertical asymptote.
Whoa, hang on now, number 4. Gotta find, guys, and we're abbreviate here the vertical asymptotes, and we should be able to quickly tell me. In fact, I think I have them drawn already.
Yeah.
They're at 2 and -2. Partial credit. Now the next part. This is what my student back there was asking me.
Determine the horizontal.
Where, how do you find the horizontal, Professor? Here we go. Now, I'm gonna stop. Give you some hints, then come back to it. After horizontal, what was it asking next after the horizontal?
Are there holes on the ground?
Oh, are there holes on the graph? And after that, what was next?
That's it.
That was it. If we can get down to that hole on the graph, we'll find, we'll be ready to graph this thing. Guys, if we go back to it before I finish it up, please tell me. This one, the horizontal asymptote, was the x-axis. My first, most basic function here. Please answer these questions for me. What's the limit as x gets large of this function, 1/x, based on this graph? I have this picture, I have this graph. As x gets large means you're going this way forever. As x getting large. What's my orange graph doing?
Rising.
No, it's not.
Is that would be 0?
What's it doing? I see some hands going up. I'm pulling this, by the way, guys, when I grab a hold of this right here, this, and start pulling the graph this way, is that. You're making x go out further and further and further. That means x is approaching infinity. I want to know what is my 1/x, which is my graph. What do you think it's doing? As I pull it out,
Constant?
look for an answer here.
Getting smaller.
It's getting smaller and smaller and smaller. Are you telling me it's getting closer and closer and closer to the x-axis the further I pull it out?
Yeah.
It's going to get really close to the x-axis. Now, why? Way out there, let's draw a number way out there on the x. Suppose I replace x by a large number. X by, where am I? I get 1 x. Replace x by 10. It's 1/10.
Oh, yeah, that
If
would
I go a little further, put 100 in there, it's 1/100. If I go out a little further, put 1,000 in there, it's 1/1,000. Are those values getting smaller?
yeah.
1/10, 1/100, 1/1,000. Go out to 1,000,000, 1/1,000,000. Am I getting smaller numbers? So I'm approaching 0. So this thing is approaching 0, and therefore, there's my answer. On this, let's approach limit, back on this graph here, negative infinity of this. Now, that would be, since I have the graph in front of me, you taking a hold of the graph here, the orange graph, and this time I'm going to pull it this way forever. That's pulling toward negative infinity. Keep pulling this. Where do you think my orange graph, or how's it behaving? The graph itself.
Also 0.
Is it going up closer and closer and closer to the x-axis?
Yeah.
Will it ever get there? No. Now why? If I place some numbers in here, like, try to find here, negative numbers, like -10, it's -1/10. Put a -100, -1/100. Put a -1,000, -1/1,000. Those numbers are getting smaller and smaller and smaller, aren't they? On the other side, they're approaching also 0. Now if I can find, that's called end behavior. You have end behavior on your test on Wednesday, but you have it for a polynomial function. Now I'm doing end behavior on a rational function. So guys, this is much like this. What is my graph doing out on the ends. And we're saying it's approaching zero on both ends. That's why the horizontal asymptote is at zero. That will tell me the location of the horizontal asymptote. Same thing may be happening on this one when I get back to it. Okay, let's try to find it. Here we go. Horizontal asymptote, let's go back to my function. Where's my function? Right here. Here we go, guys. I gotta find the limit. Good luck. As I make x get large on that end of my function. And we'll write the function like this. And what that answer is, that tells me where I'm going to place my horizontal asymptote. It's getting tough. I see by looks on faces like, whoa. Now, I don't know whether anyone in this class, Mr. Park, I may ask for your assistance here shortly. I'm going to rewrite this like this, guys. Sort of lead into it. I'm going to give you some shortcuts later on. I'm going to write in that form. This says, please replace x by some large number. Now, if you have the patience, you may say that's what it means. X is getting large. So just give me a large number at random. Some students may say, Professor, put 1,000 in there. Put 1,000 in for x to get an idea. I know it looks messy. On top here, I think is 999. Here, I think it's 998. The second factor, I think it's 1002. I think. Does anyone think they know those numbers are large? Does anyone think they know what that might be getting close to or not?
0.
Samantha says, Professor, you've got some crazy numbers up there, but I think if you actually calculate that, that is close to 0. Samantha, how'd you guess that?
Because although the numerator is a high number, the denominator multiplies, you're going to get an incredibly high number.
Exactly.
Meaning that the higher the denominator is, the closer it is to 0.
Exactly. Oh, by the way, just out of curiosity, these two are close to one another. So if I'd say cancel them out, which I can't, but they're close, would this be close to 1 here if I cancel these?
Yeah.
It's not quite 1, but it'd be close to 1. That would give you then 1 over 1,002. Is 1 over 1,002 a small number?
Yeah.
Is it close to 0? It's probably a decimal. And Samantha says, Professor, I think all this mess tells me this is close to 0. That's this. In behavior. Now the other end. Limit as x is approaching negative infinity. Same function. Go ahead and write like this.
Professor, I have a question.
Go ahead.
Because we already found the end behavior of the function in general, can we just attach that?
Oh, you mean because I've already found it in one spot there. We got
Right,
0.
because here you're gonna get the same.
We'll see, we'll see. I just want to confirm something. I know exactly what you're wondering about. I want to confirm something. Guys, this says now take this and replace all those x's by some negative crazy number. Like, give me a crazy number. I tried 1,000 on this one. Let's try maybe a negative 1,000. That would be x is approaching negative infinity, a negative number. Negative 1,000 subtract 1. Negative 1,000 subtract 2. Negative 1,000 plus 2. Does anyone have an idea what, even though those are crazy numbers, what that might be close to?
So it will be 0.
Is that value going to be close to 0 again? This. So I checked the end behavior on both ends. Is it close to 0 on both? So I'm going to accept my horizontal asymptote as right for the y. It's 0. Oh, oh, oh. Oh. Now, I gave some numbers. Now, let me show you what I would suggest, since you're moving into Math 7. And I'll give you a shortcut later on, but right now with Math 7 coming up for us. Guys, let's go back to the original function. Here it is. I'm gonna modify it. First, look at the original function. I'm trying to answer this over here again.